Good evening, everybody. As I said, today we will talk about sample midterm exam. But when I was looking at the YouTube channel, I found that there is a solution of another sample midterm exam. It means that for this semester, when I solve this, you would have access to two sample midterm exam for the fourth one. This fourth midterm exam, similar to your exam, covers everything in lecture number 20 up to lecture number 25, which is basically stress and strain transformation, pressure vessels, and combined loading. The difference between the questions that we have in the fourth midterm exam compared to the previous question is that the questions are more conceptual. What does it mean? It means that you can find the answer of the problems without solving them, without doing the numerical calculations. If you understand the concept and if you know how to deal with different problems. I will go over all these questions similar to what we had before. I will start with solving easier problems, then I will get to the problems that requires more steps. Question number 1 is a very typical question. It says, which element represents principal stress state? I remember we had this question as a practice problem in class. The answer would be the right one, E. The reason is, at the principal state of stress, we don't see any shear stress. So that's it. As simple as that. As you see, this is a conceptual question. Let me start solving problems from the bottom. This is the way that I actually prepared the solution. Question number 3. Consider a point in the structural member that is subjected to plane stress. Normal and shear stresses acting on horizontal and vertical planes at the points are shown. Sigma y is 24, sigma x is 45, and tau xy is 8. Determine the angle theta s corresponds to the maximum and plane shear stress. Okay, we just need to plug the values into the equation. The question is, what are the parameters that we need to plug into that equation? To determine that, there is one equation. Tangent of 2 theta p is tau xy divided by sigma x minus sigma y over 2. And the parameters that we have over here, tau xy is negative 8, following the sign convention that we had for stress. Sigma x is positive 45 because that is tension. And sigma y is 24 positive KSI. So I plug the values here, and once I do that, I will get 2 theta p equal to negative 37.3. One thing that I would like to highlight here is that do not forget that 2 multiplication there. That gives us the tangent of 2 theta p. Okay? So theta p would be negative 18.7. But I don't see that 18.7 over here. Why? Because that is theta p that gives me the principal stress. But I'm looking for theta s, the maximum absolute shear stress. And that would be equal to theta p plus and minus 45 degree. And if I do that, I will get these two numbers, 26.3 or 67.3. One of them is negative, the negative 67.3. All right, so the answer would be A. There is another equation for theta s that gives you directly that, but because I don't want to bombard you with lots of equations, I usually work with this one, then I will get theta s by adding or subtracting 45 from that. Okay, question number 2. I'm tired of all these parallel shear stresses on the xy plane. How can I reduce the shear stress? And how can we reduce the stress? It basically asks, how can we reduce the shear stress? We need to move toward the principal stress, because in that plane, the shear stress is 0. So simply by rotating plane surface to where there exists principal stresses, option C. All right, feel free to ask questions if you have any. Question number 6. The strain components epsilon x, y, and gamma x are provided. The situation is plane strain. Determine the magnitude of maximum in plane shear strain at that point. The maximum in plane shear strain relates to the principal strains. So first we need to determine sigma p1 and sigma p2. This topic, the questions that we have in this chapter, in this page, are actually relating to the concept that we discussed on lecture 21, I guess. Yep, this one. So here, it depends on what are the stresses. So if principal stresses or principal strain have opposite sign, the maximum in plane and the maximum absolute value are equal to each other, okay? But if they have, as we see here, if they have the same sign, either positive or negative, the maximum in plane is calculated from this equation, and the maximum absolute is calculated from the bottom equation. Okay? So this is about that concept. What is the absolute maximum shear stress, and what is the in plane maximum shear stress or shear strain? So getting back to this, we need to determine principal strain. Epsilon P1 and P2 are calculated from this equation. One thing that I would like to highlight here is that when we are working with this equation for strain, don't forget this divide by 2. This is something that sometimes students are forgetting that. So if I plug the values into that, I will get 521 and negative 589. These are the principal strain because they have opposite sign, a maximum in plane shear strain and the maximum absolute shear strain are equal to each other. Okay? So here, the maximum in plane would be epsilon P1 minus epsilon P2 over 2. And that would be half of gamma max. So gamma max is difference between the principal strain. And that would be 1110 microepsilon. So that would be B. All right? Question number 5 follows the same concept. Consider a point in a structural member that is subjected to plane stress. Normal and shear stresses acting on the horizontal and vertical planes at that point are shown if sigma x is 15, sigma y is 18, and tau xy is 30. Determine the radius of the in-plane Mohr circle. The radius of in-plane Mohr circle is another name for maximum in-plane shear stress because we know that the radius of the circle is equal to the maximum shear strain, maximum shear stress. So it means the maximum in plane, and similar to what we had before, we need to determine principal stresses. Sigma P1 and sigma P2 are calculated from this equation. Note that for the principal stress, we don't have tau xy divided by 2, but for shear strain, we do have that divided by 2. I just wanted to highlight this. Okay, if I plug the values, P1 would be 46.5. P2 would be negative 13.5. It means that the absolute and in plane are equal to each other. And that would be equal to the difference between these two divided by 2. And if I plug the values, that gives me 30 KSI. So that would be option D. Okay? Question number 4. Again, it follows the same concept. Here we have a Mohr circle. And we assume that each grid counts for 4 megapascal. Determine the magnitude of the maximum in plane shear stress. Again, it's a maximum in plane in that circle. Here, because two principal stresses they have opposite sign, one of them is located on the right part, another one is located on the left part of the axis. So simply, the maximum in plane and the maximum absolute values are equal to each other, and that would be equal to the radius of that circle. How much is the radius of that circle? We can count the grids. From what I see here, I can count 8.5, multiply that by 4. That gives me 34 megapascal. The closest answer in that option, in that list, is 34.2, so I will pick it up. Okay? Questions? So everything that we saw here is about that principal stresses and principal strains and how they are related to the in-plane and absolute maximum absolute maximum shear strain or shear stress. Okay. Look at this problem, question 7. It has the same concept. It is actually the same question as the previous one, as question 6. In that question, we asked how much is the maximum in plane shear strain, And in this question, we ask how much is the maximum absolute shear strain. How much is the answer for this one? That would be the same as the previous one. So 1110. We don't need to solve that. Okay? Okay, let me go to the bottom. Question number 9. This is a very typical question. It's a very important question because it depends on how to calculate theta, how to calculate the angle that we need to for stress transformation. Before talking about that, let me show you what part of the course relates to this. It should be in chapter 20, I guess. Yes. Okay. Do you remember this summary page, this example page, and this summary page? This page over here summarizes the concept that we need to answer that problem. The point is, when we want to use the stress transformation, we need to know what is the angle and what equation should we use, sigma n or sigma t. Again, there are two questions, what is theta and what equation should we use? And remember, there are always two ways to answer these kind of problems. If we consider the top or the bottom part, we work with sigma t. If we consider the left or the right part, we work with sigma n. The clockwise movement is considered to be a negative and counterclockwise is assumed to be positive. Okay, this is what we have learned by looking at these problems. So knowing this, now let's get back to that problem and see how we can solve that. How can we solve that problem? So for this problem, we want to determine how much is the shear stress at this plane. Okay. Again, there are two options. I will just discuss about one of them. You can work on the other one. Let's assume that we have the stress on the top surface and we want to rotate that all the way to that orange plane. How much that should be rotated? 65 degrees. Is that clockwise or counterclockwise? It's counterclockwise, so that is positive. So theta is 65 positive. Which equation should we use here? Sigma n or sigma t? Because we are starting from the top surface, we should work with sigma t. Okay? Now, let me first write down the parameters that we have. So stress transformation is this equation. We need to determine what is theta and which equation should we use. Here, actually, we are looking for the shear stress. And for shear stress, it doesn't matter which plane we start with. We work with the same equation. So sigma x is negative 7.4 because that is compressive. Sigma y is 22.9 positive. And tau xy is 9.3 with negative sign because of the sign convention we have for shear stresses. And if I plug the values here using this positive 65 for theta, we will get 13.3, and the closest answer is 8. So I would recommend you to review those two pages. Those are easy to learn, but we need to remind them and make sure that we remember them during the exam. All right, question number 8. Question number 8 is kind of similar to the concept that we discussed about. In that problem, we discussed about stresses. Here we discuss about strain, but following the same concept. A thin rectangular plate that is shown here is uniformly deformed such that epsilon x is 878, epsilon y is negative 510, and gamma xy is 680. Determine normal strain along the BD plate. Simply, it asks you to rotate the strain and determine how much is the strain in that angle. So we need to see what is theta and what equation should we use. Okay? Here, again, there are two ways to solve this problem. Here I assume that I'm starting from the right surface, and then I rotate that like this to that plane. Okay? Here, again, the theta is counterclockwise, so that would be positive. How much is that theta? It is not given, but we can determine that. Tangent of theta is 108 divided by 72, which gives us 56.3, and I simply plug that into strain transformation equation. This is actually epsilon n because I have started from the right. So I just plug the values and I will get this number, which is D. Question 12. The strain components, epsilon x, y, and gamma xy, are given for a point on a free surface of a machine. When we talk about the free surface of a machine, it means that that is a plane stress situation. Okay? So we use the equations related to that part. The modulus of elasticity for the material is 14,000 ksi, and the Poisson's ratio is 0.32. Determine stress sigma x. What part is that related to? It is a part of generalized Hooks law. So in this page, we can see summary of all the equations that we need for generalized Hooks law. Okay? Again, just to remind you, the equations that we see on the left part of this slide are generalized three-dimensional stress-strain relation. We usually don't work with these equations. Okay? We usually work with the simplified case, which is plane stress, which is shown here on the right top part. So equations on the left part of that, I mean the left part of here, which is epsilon x, epsilon y, epsilon z, are giving strain as a function of stress. Equations on the right are giving stresses as a function of strain. Okay? For that problem, strain are provided. I just plug the values into that equation. This is the equation that we have as a generalized Hooks law for plane strain situation. And I just plug the values that we have in the problem statement, and that gives us the answer. That's it. Okay? Question number 11. A half an inch thick titanium with a modulus of elasticity of 14,000 and the Poisson's ratio of 0.32 plate is subjected to biaxial stress. Sigma x is 25 ksi, sigma y is 82 ksi. Determine the change in the length of edge AD. Again, we need to use the same equations that we discussed. We need to go to the generalized Hooks law. When we are talking about the change in the length along the AD, it means that we need to know how much is strain in that direction. Once we know how much is strain, we multiply that by the initial length to get the deformation. Okay, let's do that here. Strain in that direction. Here is the plane stress situation again. Why? Because we are working with thin-walled elements. For thin elements, that is always plane stress situation. So epsilon y is 1 over e sigma y minus nu times sigma x. And I just plug the values that we have in the problem statement. And I will get epsilon y equal to 5286 microepsilon. Then multiply that by the initial h, the initial length, to determine how much is the change in the length. Initial length is h, which is 4.5 inch. And that gives us 0.238 inch, which is option C. Question 10 is strain rosette problem. This is a very typical problem. I guess you will see at least one question from this part. These questions are very straightforward, but they are a bit time-consuming because they require solving a system of equations, three unknowns. Again, I would recommend you to learn how to use your calculator to be able to solve these kind of problems quickly. Let me show you the part of the course that describes this. Okay, so strain rosettes are discussed here. This page summarizes the equation that we need for solving strain rosette problems. The basic things that we need to do is we need to form a system of three equations and three unknowns because in strain rosettes we have three gauges. The only tricky part is what are the angles that we need to put into these equations. And the way that we determine the angles is we determine the angle from the positive direction of x. That's it. Once we determine the angle, we put that into this equation and we repeat that for all gauges that we have, and then we solve the resulted system of equations. How much is theta for strain gauge A? It's 45. It's very straightforward. So I plug the values there. The reading of that gauge is 754, and if I plug the values, I will get these numbers. How much is theta for gauge B? 90 degree. So once I plug the values, I get this number, this equation. How much is theta for gauge C? That is 135. It is not 45 because that is measured from the positive direction of x. So once I plug the values, I will get a system of equations. And if I solve that, we get epsilon x equal to 694, epsilon y 2090, and gamma xy negative 476, which gives us option D. Let me tell you a trick for solving these kind of problems. What if I ask you to determine how much is the strain reading in the y direction? In that case, we didn't need to solve the problem actually. Why? Because we already have a gauge which measures the strain in that direction. Okay? So whatever that gauge reads is the strain in that direction. We sometimes have this kind of tricky questions. In that case, you don't need to form a system of equations. You can quickly determine what is the answer of those problems. All right?